So, this short talk is on Heisenberg uncertainty principle, and it originated from a quiz question that I had given in my online course, and the question reads as follows. A particle has a certain wave function. We measure the position of the particle so that it becomes known within an uncertainty of 10 power minus 18 meter. So, a particle has certain wave function, and then we make a measurement of its position, and because of that measurement now we know that its position is within this range, and the uncertainty is in position is 10 power minus 18 meter. So, with this accuracy we know the position of the particle. The question goes ahead, then we measure the momentum of the particle and it becomes known within an accuracy of 10 to the power minus 18 kg meter per second. So, after this we make a measurement. So, we have a wave function, particle has a wave function, then we make a measurement, position measurement, and when we do this position measurement we come to know about the position with this uncertainty, and then we make a momentum measurement. After this we make a momentum measurement, and then we get this uncertainty in momentum, and that is 10 power minus 18 kg meter per second. So, since I am doing the measurement, of course, I will know the value, and depending on the accuracy of my experiment the value will not be exact, will have some range, some uncertainty there, some error there. So, these are the things. Now, the question was, there were 4 options, but the main question was that the above 2 measurements do not violate Heisenberg uncertainty principle, yes or no. Okay. Because if you take this as delta x, this as delta p, and if you multiply delta x delta p in SI units, it becomes 10 power minus 36, right. This is in SI units, that joules second or whatever. So, but then if you look for h, which is something like 6 into 10 power minus 34 in SI units, and divided by say 4 pi is around 10. So, this will be this is divided by 10. So, this will be something like say 10 power minus 35, and here it is 10 power minus 36, right. So, it is less than this. So, does it violate Heisenberg uncertainty principle? Now, in my course many of the students have given the right answer that it does not, but the reasons given are ambiguous. One big chunk is which concentrates on the word then. First measurement is here and then the second measurement is here. So, the 2 measurements are not simultaneous, and according to them what they think, the notion is that for Heisenberg uncertainty, when we are saying delta x delta p, the 2 measurements should be done simultaneously. The 2 measurements should be done simultaneously. In the same measurement I should get delta x, and in that same measurement I should also get delta p, then this holds. So, that is one answer that I got. Another kind of reasoning was that since they are in 2 different states, because when we measure this position the wave function changes from psi x, the wave function here becomes psi 1 x, and the momentum measurement is made on this state. So, delta x is in one state, delta p is in some other state, and therefore, Heisenberg uncertainty principle is not applied here. In the same state you should have delta x and delta p. So, that was second line of reasoning. So, these two were the main streams, okay, and therefore, I want to clarify certain things. When we say Heisenberg uncertainty principle, it originates from the wave character, right. We have a wave function. So, whenever we have a wave function, the wave function is represented by some function, and if you allow me to plot, it could be something of this sort, and after that it is very small. Now, in this kind of wave, without doing any measurement, we know that this is the position can be here, the position can be here, the position can be here, here. If the wave function is now very small, negligible, okay, there is no probability of finding the position there, but then as long as the wave has some significant amplitude, there is some probability. That is the uncertainty we are talking of. In Heisenberg uncertainty principle, the delta x that we are talking of is not if I make the measurement, after the measurement what is delta x, that is decided by the experiment, the technology, the methodology, in the skill with which you are doing the experiment, those things will decide that delta x. But even before doing the experiment, if I want to predict, if I do the experiment, what will be x? And my answer will be, okay, x can be this, x can be this, x can be this, x can be this. That is the uncertainty we are talking of. And similarly, momentum. Now, this particular wave function is made up of or can be obtained from superposition of a large number of plane waves extending from minus infinity to plus infinity with a fixed lambda. Okay. So, I have a wave like this, and then I have a wave like this, and so on. These are all extending from minus infinity to plus infinity, that means large extents, and this has a particular momentum, this has a particular momentum. But when you superpose all these and get this, then in this wave function you have this momentum, in this wave function you have this momentum, in this wave function you have this momentum, and so on. And therefore, before doing the measurement, remember, before doing the measurement, if I ask you what will be the value of p if I make a measurement, then you will say it could be this one, 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 and therefore, there is an uncertainty delta p, and it is this delta x into this delta p which has a lower limit. If you have defined it properly in terms of that standard deviations and all that, that should be, the lower limit is h cross by 2, so there is a lower limit. Now, if I come to this question, when I made the measurement, it becomes psi x, and when I again made the measurement, it becomes psi 2 x. When you make a measurement, you change the wave function, because suppose this is it and I make a measurement, I physically make a measurement, and I find that, okay, within my accuracy of the experiment, the particle is from here to here, somewhere here. That means now the wave function of this particle after the measurement should be almost 0 here and almost 0 here. It had very significant values here, okay, which now becomes 0. So, the measurement has disturbed the system, the wave function has collapsed and changed from psi, it has become psi 1. And similarly, when you make a momentum measurement, again you change the wave function and this psi 1 becomes psi 2. The information that we have is, in psi, if this is the wave function, then this is delta x, and if this is the wave function, then this is delta p. Okay. So, if this is the wave function, if you want to make a measurement of delta x, yes, you can do that, and it is this. And if you have this wave function and you want to make the momentum measurement, then this will be delta p. and therefore they are not related with this Heisenberg uncertainty principle, which says that delta x times delta p should be greater than equal to h cross by 2. Even if I come up with the same state again, suppose I have made a position measurement and then okay, I do not make a momentum measurement here, but I again prepare my particle back in this state, and then make a momentum measurement. Even then I am not going to get this delta x into delta p, because single measurement there is no limit. Single measurement you can always do, right? You can, if you have a wave function and you want to make a measurement and then ask how accurate I can measure the position.